Hey everyone, thanks for coming. So thanks for the introduction. Yeah, as you said, my name is Nitschinger. I work for Couchbase as a software engineer based out of Vienna. And I'll talk to you a little bit about Spark and Couchbase. So even if the light is a little bright here, let's do a quick show of hands. So I'd like to categorize a little bit. Who is a data scientist and doesn't really know about like running databases and doing back-end engineering? Okay, a couple. And who is like me and is quite versed in back-end systems and is here to figure out what the hell machine learning and all this stuff is? Okay, awesome. So, as I said, I fall into the second category. And what I'm trying to do in this talk is give you an introduction into Couchbase, but also how you can take an operational data store. It doesn't have to be Couchbase, but of course, you should probably want to use it. And show you how you can use it together with Spark and get the operational side and the analytics side merged together and benefit from it in your business case. So for those who don't know Couchbase, Couchbase in a few words is a document-oriented database which allows you to scale linearly so you can add and remove nodes on the fly. We provide key value access, all kinds of secondary indexing with a SQL query language called NoSQL, which I'll talk about in a second. So for now, think of it as a document store that is distributed and basically scales a little bit the same way that Spark does, right? So why Spark and Couchbase in the first place? Why are we even here today, right? So I think if we take it to a higher level, and we'll get to the technical side of things very quickly, but if we drill it apart a little bit in terms of use cases, now, from an architectural point of view, we have a cluster of Couchbase nodes, and then we have a cluster of Spark workers and executors and so forth. Now, for example, if you store your catalog data in Couchbase, then you can use Spark with it to do recommendations, right? You can build powerful recommendation engines. If you have personalized data in your data store, you can do predictions, and in mobile applications, you can do fraud detections and other things. But the key takeaway here is that very often you have a primary data store, right? And very often it's a relational database. But I talked to many people today here, and they also told me that, well, yeah, we store our data in a SQL Server and in an Oracle and whatever, but it doesn't really quite scale with what we need together with Spark, right? So Couchbase, with its performance guarantees, provides a viable alternative here. So we have our primary data store, and then we perform on our analytics in a Spark cluster, and we hook it up with the Spark connector that you'll see in a second. Now, if we look at one specific use case, that is operationalizing analytics and machine learning. So the main goal here is, of course, we need to train our machine learning model, right? So very often people have the data in a data warehouse or in a Hadoop system, right? So they use this historical data to train their models. But when it comes to actually serving the requests in real time from a front-end system, imagine you're building like a shopping cart or whatever, right? A retail system. You want to, in near real time, use those, basically query the model, get the predictions, and then return it to the user in real time. Now, as it turns out, you can't do that with Spark alone, right? You need a system in the front that is able to serve your requests in micro and millisecond latency, but still giving you all the guarantees you need from your data store. And this is, I think, where the sweet spot is when it comes to operationalizing analytics, right? You want your operational data store and your Spark cluster working hand in hand together and also deploying them together if you want to. Now, the other very interesting topic or use case I see is that I always call Spark the Swiss Army knife of data integration. Because there are so many different sources available for Spark, it's trivially easy to pull data out of HDFS and join it together in a data frame with Couchbase data and then store the result back into a different system. And doing all of this with the powerful abstractions in Spark, especially with data frames, I think this is a very interesting use case. So imagine you have your primary data in a NoSQL store like Couchbase, and you read it, basically you write it into Spark, and then you munch it together with data from HDFS, S3, Elasticsearch, whatever. Then you write the results back into Couchbase or a different system. So these are the two use cases we see the most out there when people ask, how can we make this work, right? Before we drill into the technical details of the connector and how it all works together, I quickly want to mention the deployment scenarios because there are many vendors out there who say you can run Spark on platform X. Now with Couchbase it's different. Couchbase is a database like SQL Server in that regard, so that it runs as a standalone system, and you can deploy Spark alongside Couchbase, but you can't deploy a Spark application into Couchbase, right? Couchbase is written in Erlang, C, and Go, so there is no JVM where you can send your jar into and make it work magically. So you use your Yarn setup or your Mesos setup, but you can use different approaches how to approach it, right? So the first thing is you can run them basically separate. So you have your Couchbase cluster with X nodes, and then you have your Spark cluster with Y nodes, and they just talk to each other over the network, right? This is fine, especially in smaller scenarios and where probably the data analysis part, so where you need to do the heavy lifting, the data crunching, is more important or takes more resources than the network traffic. But the other side is that when you actually need to move lots of data around, right? This is typically in data integration, right? I'm siphoning, I don't know, gigabytes out of my HDFS, do something with it, and then store it back into Couchbase. If you want to do that, then doing a side-by-side deployment is very often a good idea because, as we'll see in a bit, we provide for our key-value operations, we can basically give Spark location hints and say, you want to fetch this document? Oh, it's actually on this node, and then Spark can deploy this operation directly on this Spark work, and then it basically can avoid the shuffle operation. It doesn't need to go over the network. It can fetch it over from localhost, and it's more performant. So talking about access patterns, how can we access data from Couchbase and move it into Spark, or the other way around, take data that we've computed in Spark and move it back into Couchbase? So the first and most performant way is by key value. So Couchbase, from its history, came from a cache-oriented background. So we still support key value and the notion of a document with a unique document ID per bucket, and a bucket is basically like a database. So every document inside a bucket is unique, right? Identified by its ID. And as you know, key value lookups are very, very performant, right? And we partition the data automatically to scale out linearly. So you can fetch and store the document by its ID. Now, that alone is not very, I mean, it is fast, but it's not flexible. And as a result, we introduced what we call the NoSQL query language, which you can think of for now as SQL with extensions for JSON, right? And the reason I said JSON is because if you store JSON document in Couchbase, you can use all those secondary indexing querying mechanisms that we have available. So you can even store binary data and JSON side by side. If you store binary, then you can do it via key value, and for the other stuff, you can also use the NoSQL query language. And then we also have MapReduce views, which were in Couchbase long before we had NoSQL. So NoSQL superseded most of its use cases, but because MapReduce is pre-aggregated, or basically pre-stored data in a B tree on the server side, aggregations are very, very performant over the whole system. So there are still use cases for MapReduce. But honestly, most of the time, you'll find yourself using NoSQL and key value. And then we have streaming. So Couchbase is a distributed system, and it has a replication protocol internally. It turns out we can reuse that replication protocol to provide Spark D streams and even structured streaming, which is supported in Spark 2.0, to feed mutations as they happen in your Couchbase server directly into Spark and then perform your analysis on top of it. And I put it in a different color because it's not yet released, but we're also working on full text support. If you know Elasticsearch and Lucene, this is very similar. And in the future, we'll also have support for full text search directly built into a Spark connector. Okay, so that's great, but how do we actually, what do we do with it in Spark, right? So for key value, we can basically create RDDs and also store RDDs. Now for NoSQL, RDDs also work, but given that we have a structure of JSON and we have a great query language, there's probably something we can do better, and that is SparkSQL. So we have SparkSQL integration. You can create data frames and data sets directly from your queries outside of Couchbase. MapReduce views support RDDs, and the streaming part supports D-streams and structured streaming. Okay, now if we start from the simplest part, which is our key value operations, how do we shard the data? As I said, Couchbase is a distributed system. Now, what we do is we have a bucket, right? And a bucket is like a database, which is a logical grouping of our documents. And what we do is we slice this logical grouping up into 1024 partitions, and then we distribute those partitions on the cluster. So if you add or remove nodes from the cluster, the cluster manager will basically rebalance those partitions on the cluster as an online operation. So you can do this while keeping your jobs and online traffic running. And what happens on the client side is that we do this hashing based on our document ID. So the client knows basically which document the server maps to, and that we don't need like a sharding server, right? The client always knows where to go directly. It's basically hashing and then lookup, so it's always fast and performant. Now, what can we use this for in Spark? We use this for data locality. So for key-value traffic, we provide location hints to Spark as a transparent operation. So we fetch the cluster map in the background, and then every time you are reading or writing a document for an RDD, we tell Spark, okay, the preferred location is this host. And if you deploy your Spark workers alongside the Couchbase nodes, then Spark can send the operation directly to that node. If it's not there, well, it doesn't matter, right? It's just a hint, it's not a requirement. Note that this is not available for Nickel and Fuse, and the reason is that Nickel and Fuse basically round robin, and if you think about it, if you do a query like select star from whatever, it is fetching many documents in the background, so there is not a single node we can point it to since this is a distributed system. And as a result, for Nickel and Fuse, we basically do a round robin approach to all the available query nodes, which in turn then talks to the indexing stuff in the background. I'll show you how that works in a second. So what about Nickel? Nickel, as I said, is like a SQL service. I always say like, but it is very similar to SQL. We just don't implement a specific standard. But the syntax that you'll also see in a bit looks very familiar. But it also adds JSON operators on top of it. Since we are dealing with unstructured data, you can imagine you have nested objects inside arrays and so forth in your document. So we provide operators to perform manipulation. So you can use, for example, unnest to move data out of an array into the top level. And we also provide joins. So you can use joins, you can join documents together, and you can also join inside a document, right? So there are many ways, and this gives you lots of flexibility for data modeling. We, as an indexing structure underneath, we use what's called Couchbase Global Secondary Indexes. I don't want to go into all the details, but it's a very efficient way to stream data with our internal replication protocol, which is memory to memory, directly into our indexes, and then the query engine can basically query it from there. It runs on any node in the cluster that you define, and you can add and remove nodes on the fly, right? That's part of our scalability. So if we look at this query architecture, so and each of those pictures here, basically, it can run on the same node, but it doesn't have to be, right? It's transparent to you. You can just say on this node, I want the data service and I want the query service, and you can choose that freely. Now, here we have our bucket data, right? This is where our key-value traffic happens. And then there is a component which is called the projector, which streams the data into the indexer. The indexer then updates its indexes, stores it in memory, and also persists it into disk. And then at query time from the query service, based on its query planner, figures out which index it should use, and then it talks to the indexer and grabs the data from there. If you have a covered index, then it can stream the results back directly. If it's not covered and it needs to fetch documents, it does key-value fetches in the background, fetch the document from the data service, and return to the results right away. So how do we implement this in Spark? If you implement a data source, I don't know who've seen yesterday morning, there was a talk on implementing a data source. And he mentioned part of this here, and I want to reiterate quickly. So if you implement a data source, depending on the different capabilities, you can implement different interfaces. So there is a table scan, a pruned scan, and a pruned filter scan. And this one is the most flexible one. This is also the one we implement. So what this means is basically if you do a SparkSQL query, Spark pushes us down the list of, basically the list of attributes you want to load, and also the where clause, right? But what it's not pushing down is, for example, aggregations, joins, and so forth. So even if we could do it, currently there is no way for Spark to push this information down to us. So we hope in future versions this will be improved and give us more flexibility, so we could even push even more down to the database, which means less network traffic, and so forth. So this is how it looks like in code, right? So on the left side you see, and this is I think half the match clause. you see all those predicates that Spark is basically passing down to us, and we are converting them into nickel, right? So this is basically a nickel string created. You can see like clauses and contains and all kinds of SQL-ish stuff here. Now, another interesting thing is schema inference. If you think about JSON data, JSON doesn't have a schema, right? Every document can look different. So how on earth are we handling schema? Because every data frame needs to have a schema. Well, there are two approaches. We provide automatic schema inference, and you can provide your own schema. And the idea is always that the schema that you provide is basically larger than what you're expecting. So if you have attributes in your schema and the document that you get doesn't have those fields, then they are nulled out. Right? And if you provide a smaller schema, let's say a document comes along which doesn't have the fields you provide in the schema, well, they're just discarded, you don't have access to them. But that's the idea, that you can basically have flexibility on the schema while not enforcing some kind of schema onto you. Now, okay, how we are dealing with this in practice, because imagine you have a bucket of 5 million documents and 15 different types. In our database, we have a sample data set which is called the travel sample, which contains airlines, airports, reviews, so forth, right? And every document looks different. So how can we make this work in practice? Now, what we see here is actually automatic schema inference. And the trick is you provide a predicate which identifies the type, right? In this case, our JSON document has a type field where the type signifies the type of our document. So type airline would signify an airline document. And this thing here is turned into where clause, and we'll see in a second how that query looks like. And that where clause is always used going forward. So here we are creating our data frame, and we know, okay, our airlines, and we know that the type equals to airline, identifying our documents. And then we perform data frame operations on our data set, as you know from SparkSQL. Now, so we have 1 and 2 queries here. So how do they look like? This is from the log that when you run the application, you'll see dumped out. So this is our schema inference. You can see, I'll explain this weird meta thing here in a second. Select meta ID as meta, travel sample star from travel sample where type equals airline, limit 1000. So in a nutshell, what we're doing is we're fetching 1000 rows with the predicate that we provided on the last slide, and in addition to fetching all of the fields, because we want to find out basically the biggest schema that we get there, we also select meta travel sample ID. And this is nothing else than, as I told you before, we have key value, right? And the key, the document ID, is not part of the actual value structure. And with this meta function here, we can also extract the ID. And this is very useful because very often you want to fetch documents, do something, and then you want to store them back into Couchbase, but you need the document ID. And because it's now part of the data frame as the meta ID column, you can always access it and use it later for storage. And now here's basically the query here. Select name call sign, sorting show, turns into this query. Select name call sign from travel sample where type equals airline. So the first observation is, hey, we dragged our type equals airline forward, right? It's stored and always used since this is our predicate that signifies our types. But we also see that name and call sign are passed down from Spark into Nickel, so we only select the fields that we need. What you see, what is not happening, the sorting is not pushed down from Spark. And this is because Spark right now is not able to tell us what kind of sorting we want, right? So we return it all records unsorted, and then Spark needs to sort them again. So there is room for improvement there in future versions. So how does this schema look like once it's inferred, right? This is how the schema would look like for this airline document. And if you, for example, if you know, okay, my data set is so diverse, I can't use schema inference, you can always provide the schema manually and override it, right? So if you know I want this specific schema, then you can always use that. Okay, so that's about SparkSQL. And now let's come to something very interesting, DCP and Spark Streaming. So, as I said, DCP, which is called a short name for Database Change Protocol, is our internal changes feed. So it feeds mutations, deletions, and expirations from the master to the replica. Since Couchbase is a distributed system, it has replicas as well for failover handling. And those replicas, and also other components like the indexer you saw before, everyone is using this changes feed, so we can abstract it completely from where it is in the cluster, right? It doesn't matter if it runs on the same node or a different node, the internal components behave the same. And we use this functionality to feed data into Spark right off our masters. Now, there are a lot of things here which I can't show you right now because we don't have the time, but even if it sounds simple, it's not. Everyone who has tried to deal with streaming reliably through a distributed system, it's actually very hard. And this is why things like Kafka exist, right? Because this is a very hard thing. And the reason is you need to deal with node failures, right? You need to deal with rollbacks. Imagine you're streaming from a node here, and you're consuming up to sequence number, let's say 1024. And now this node fails, the replica takes over, but the replica only got, because it's all asynchronous, only up to sequence number 1000. So you're actually 24 sequence, or basically mutations ahead of the new master. So you need to roll back those operations, right? So there's lots of stuff going on underneath that we are doing our best and trying to hide from you, but this is very complex. And the reason I'm saying this is because we had Spark Streaming support as experimental in the driver for over a year now. But we used a different implementation. We now switched to a standalone library that we are developing separately, which is now also used by the Kafka connector and other integrations, like there are great guys from Italy doing Neo4j integration and so forth. So we pulled it out as a standalone library, which makes it much easier for us to develop and stabilize. So this is for Spark Streaming. And now with Spark 2.0, they introduced structured streaming. And apart from seeing a little bit of code here and there in a repository, I didn't see any like real-world full-blown implementation from a data source out there yet. But we released the Spark Connector yesterday, and it features support for structured streaming, and it works already out of the box. Now, I need to mention, of course, since structured streaming is experimental still in Spark as well, technically our stuff is experimental as well, right? So we'd like to get feedback on this. And so how does it work? So we have our DCP stream, which is feeding mutations, right? It's coming in and feeding mutations. Now, the structured streaming is basically like a data frame. It's a table, but it's an unbounded table. So every mutation that's arriving from the server is appended to our table structure, and then you can consume it from a structured stream, doing window slicing and so forth, doing all kinds of things. And one thing that is important here, we need to make a translation from JSON into the row format, right? Because a data frame is a data set of rows. So we need to take our JSON string and turn it into a row. And this is why, in this case, you need to provide an explicit schema. Because we can't do schema inference here because there is no data we know that's coming over the stream, right? So in this case, you provide your schema, and here's a sample schema, right? So this is how you define schemas in Spark. Here let's say we have a meta ID field. If you put this in, we also give you the document ID. If you omit it, then you don't get the document ID. And we just define two fields, type and name. So every time a document arrives, you get a data set with 3 columns, meta ID, type and name. If they exist in the JSON, they are filled with the value. If they don't exist, they are null. And what we also do is, if you don't provide a schema, what we do is we create a schema with only 2 columns. The first one is still meta ID, and the second one is value with a binary type. And then we feed the binary type to you, but then you need to convert the binary type to different type with Spark mechanisms on your own. So this is how you define a structured streaming source. So here we have our Spark session, and we call read stream on it. And then for the format, we say Couchbase Spark SQL, and then we specify our schema. And when we call load, then nothing happens because it's lazy, right? So we need to do something with our operations, for example, dumping out to the console, doing something else with it. That's then up to you and depending on what you want to do with the data. But what you'll get as a result here is basically a data frame with the schema that you provided. And then you can deal with it the same way you would load a bunch of JSON documents from a file or whatever, right? But keep in mind that this is all against a distributed system in the background, and Couchbase is able to run millions of operations per second. We have users who are doing that, right? So quite scalable there. And in addition to using it as a source, you can also use it as a sink. So imagine here we have the very classic word count, right? Every Spark documentation you find a word count. So imagine you did your word count and you want to store the data somewhere. So you say write stream, and then there are 2 output modes in Spark Streaming. There is, I think it's called complete and append. You use complete when you do aggregation, and use append if you want to append documents, basically, not doing aggregations. What you also need to provide is a checkpoint location. This is not related to our Couchbase integration. If you have a reliable sync, you need to provide a checkpoint location to Spark, because Spark does all the transparent checkpointing for you. And then when you have a restart, then it basically signals the source where to start from, which offset, and so forth. It's recommended that you use some kind of HDFS file system so that it's distributed and fault tolerant. And now, and this is important, you also need to set the ID field, because remember, previously, every document needs to have a unique ID. So in our case here, we set it to value. So the value of our data frame will be used as the document ID. And then we say format Couchbase Spark SQL as before. So we tell it, okay, please use the Couchbase Spark implementation. And then we call start. And then we call query await termination, and then our query starts to run. So to basically finish up here, we currently have 2 connectors. So the first one is the version 1.2.1, which is compatible with Spark 1.6 and supports datasets and so forth. So it has DCP flow control, but based on the older implementation. So, and enhanced Java API. So if you're still on 1.6, you want to pick that version. But if you're on 2.0, please go to the brand new 2.0 Spark connector, which uses the new DCP client, has support for structured streaming. Everything works as before as well, so migration should be pretty smooth. And finally, where you can find more information, in terms of resources, we distribute our Spark connector to Spark packages. It's also available on Maven Central, so you can easily specify it as a dependency in your project. When you deploy it to a cluster, you can specify it as a dependency when you run it. We also provide quite comprehensive documentation, and you can find the source on GitHub. It's all open source, like the database itself, right? You can always check out the source, and if you find bugs, please file them here. And I think I have a few minutes left for questions. Thank you very much.